David Spears, civil engineering instructor at Texas Tech University, talking about statics, CE 2301. Got some homework problems involving moment of inertia by composite method. There's the bird. The first one I did, for some reason I got them out of order. I did 822. Did it pretty much completely. It's this weird shaped kind of spirally thing that I've kind of shown with black lines through it. It's really a rectangle with two quarter circles taken out of the corners. And so, similar to what we did on that last homework, we're going to use, of course, we're going to use the parallel axis theorem a lot, but we're going to solve backwards for the properties of the quarter circles, their areas and moments of inertia, especially about their own centroids. Now we're supposed to find Ix, Iy, and the radius of gyration, and we want to use this parallel axis theorem, which is that the moment of inertia about some axis, x in this case, is equal to Ix prime, which is the moment of inertia about its own centroid, plus AD squared, the area times the distance from the centroid of the area to the axis that we're taking moment of inertia about. So first we talk about a quarter circle, the radius of r. The area is of course pi r squared over 4. And we can get from formula books and off the internet and textbooks that the centroid of that quarter circle is measured from one of the flat sides, 4r over 3 pi. Of course, being symmetric, it's the same to the y and the x-axis. And we can also get the formula that Ix, the moment of inertia of that shape about the x-axis, not about its own centroid, but about the x-axis, is pi r squared over 16. So we can use the parallel axis theorem and solve backwards. Ix prime, its moment of inertia about its own centroid, that x prime axis, or for that matter the y prime axis, is Ix minus AD squared. So Ix is pi r squared, pi r to the 4th over 16, minus A is pi r squared over 4, and its centroidal distance is 4r over 3 pi. I have to square that, and so I come up with this formula, 0.05488 r to the 4th, the radius 4th. So now I can plug into a table. Also for the rectangle shape, I'm going to use these properties. The centroid about its own, the moment of inertia about the centroid axis, Ix prime, of a rectangle of dimensions b wide and h high, is bh cubed over 12. We're going to use that number a lot. And if I rotate my axis 90 degrees to the y prime axis, it's just b cubed h over 12. Same thing. So I make a table, because I like tables because it helps me remember to do everything. Divide it into the segments of the rectangle, which is positive, which I've outlined in red, positive area of 2 by 4, so it's 8 square inches. Its moment of inertia about its own x-axis, x prime axis, through its centroid is 4 bh cubed over 12, 4, 2 cubed over 12, 2.67 inches to the 4th. Its distance from centroid to the axis I'm taking moments of inertia about is 1, because it's 2 inches high, and it's so it's half of that, 1. AD squared, dy squared is 8 times 1 squared, or 8 inches. If I continue it on, look at Iy prime, it's looking at that axis that it's centered on, which also happens to be the y-axis I want moments of inertia about. So it's just looking at the rectangle on its side is 2 times 4 cubed over 12, or 10.67 inches to the 4th. Interestingly, its dx distance from its centroid to the centroid to the line I'm taking moments about is 0, because it's symmetric about that axis. So the ADX squared term turns out to be 0. Now a little bit more complicated, I got to look at those little quarter circles. and it's not symmetric, so I have to kind of break them up into two parts. Area 2 is pi r squared. The area is pi r squared over 4 negative pi, essentially. Its own centroidal axis moment of inertia is this 0.05488 r to the fourth, which is negative. And remember, this is a negative area because it's a cutout of that rectangle. Negative 0.078781. The distance from the centroid of it, the quarter circle, to the axis, the y-axis, is 2, the height, minus that distance, 4r over 3 pi, so that works out to be 1.151. Do the AD squared term for it. The area is negative times this number squared, negative 4.16. IY is similar, but look at it. Its on moment of inertia about the y-axis is the same as the one about the x-axis. It's a negative 0.8781. Its dx distance to the centroid is that same thing, 2 minus 4r over 3 pi, negative 1.51. I'm going to square that, multiply it by the area way back over here, so I get a negative 4.16 for ADX squared. Looking at area 3, the other quarter circle, same area, same I, x prime, but this time its dy distance is only 4r over 3 pi, which is that 0.848 distance from here to here. Its ADY squared term is negative pi times this squared, negative 2.26. Its IY prime is same thing. Its dx distance is a 1.51. It's important to keep track of these negative signs on these d distances because sometimes the negative counts, but in this case we're squaring them so it goes away, so I have negative 4.16 here. Now I'm ready to do all my summations. My areas, just the sum of this column, 1.717 square inches. IX is the sum of IX, using the parallel axis theorem, IX prime, 0.9105, plus its AD squared, ADY squared term, 1.576. I get IX is 2.487 inches to the fourth. Similarly for IY, add those two columns up, 8.91 minus 8.32. I get IY is equal to 0.59 inches to the fourth. Look at it, does that make sense? Yeah, because the Y is, the moment about the x-axis is, I've got more area further away. The y-axis is really, it's centered on that, and most of it just comes from the little weird shape in the black. So those answers make sense to me. The radius of gyration is real easy, just square root of the IX, or whatever the axis is, divided by A, 1.20, 0.583. That should get you going on 821 and 828. 821 is a rectangle with a half circle cut out of it, or a semicircle. I want to start off with the properties of that thing. The area is, of course, pi r squared over 2. Its centroidal distance is that same 4r over 3 pi to the base, that flat line that makes the base of it. So, and I'm given from a formula book, Ix, moment of inertia about that line on its base, is pi r to the fourth over 8. So I work out the numbers. I didn't actually work that one out. Parallel axis theorem says Ix prime is equal to Ix minus AD squared. So I do the math and I get this formula here. So that'll get you started. So I'll break it up into two segments, get the areas. The area of the rectangle is 240, which is 120 plus 120, by 120 high, so it's 28,800. The area of the half circle is a negative area. It's negative pi r squared over 2, which is negative 10,053. Then you can figure Ix prime from this formula here, Ix, which is this number, pi r to the 4th over 8, minus the AD squared terms, where that's the area and that's the D, square it. So that's Ix prime. You can get that number on your own. dy, distance for the rectangle, is just half of 120. For the half circle, it's the distance 120 minus that distance to the centroid, 4 over 3 pi. Square them, do the math, sum those columns. Same thing for Iy. I'm taking moments about this y-axis. I've got Iy prime of a rectangle. I'm going to use this formula here. BH cubed over 12, which is what I used here. B cubed H over 12 for this Iy prime term, because I'm taking moments about its own centroidal y-axis. Do the same thing for the semicircle. Its distance from its Iy prime is going to be, I'm going to have to use, I think you're going to have to look up that formula for Iy prime. That comes from a chart. And you can get the Iy prime about its own centroidal axis from a chart. Plug that into there. Its dx distance for the rectangle is that 120. Same thing for the semicircle. Remember that it's a negative area. Square those, get that term, sum them all up. I will give you the hint that the sum of these Ix terms, Ix and Ix prime and ADY squared, is 5 something point something 10 to the 6 millimeters to the 4th. For Iy, it's some of these terms, 3 something something 10 to the 6th millimeters to the 4th. Okay, now we finally get away from these semicircles, which are hard, quarter circles, and I get this sort of 6-sided figure. These dimensions, 30, 30, 30, 30, 30, 30 wide. Break it up into 3 segments. Break it up really into 2 segments to do Ix. Here's the X prime. I want the, didn't write it down. What I want for this problem to find is moment of inertia about its own centroid. So I kind of got to break it up into 2 parts due to what I know about triangles. For Ix, moment of inertia about its own centroidal horizontal x prime axis, which by symmetry is right in the middle for both axes, x prime and y prime. The area, 60 by 60 of the rectangle. The I, BH cubed over 12, where I've got 60 and 60 for the B and H. My centroidal distance from the centroid of the shape to the centroid of the overall thing is 0, so that term goes to 0. ADY squared. For the Ix prime, I've broken it up into, I can break that triangle up above into that big triangle that's a base of 60, height of 30, and I've got 2 of them, above and below, so I can figure the area be 1/2 BH, and I can figure Ix prime from these properties of a triangle. Ix prime for a triangle of base B and height H is BH cubed over 36. So that's what goes in that term. dy is the centroidal distance. Of course, the centroid is is 1/3 of the height from the base. And so I've got to add that number to 30 to get dy. Then, remembering that I'm going to have my areas multiplied by 2 because there's one top and bottom. My Ix primes, because there's one top and bottom, multiplied by 2. And then so do the d squared times this area, which is the sum of those 2 triangles. Sum them all up, get my sum of my areas, and some of my IX primes and 80y squareds. Add those up, and that's going to be equal to 4 point something something 10 to the 6 millimeters to the fourth. Okay, due to what I know about I don't know what the moment of inertia of that triangle is about its Y centroidal axis. I recommend breaking it up into 4 2 above and 2 below half triangles shaped like this down here at 3. So the area of the rectangle is still the same, its moment of inertia is still the same. Its centroid is on the centroid of the overall area, so its dx distance is 0. For the triangle, which I've got 4 of, the area of it's a 30 by 30 triangle, so it's 1/2 30 by 30. Multiply that by 4 for this box. Iy prime is this value over here, hb cubed over 36. So multiply that by 4, plug it into that box. The dx distance is going to be this 1/3, actually in this case b, it's the same number, from the centroid of it to the y centroid axis of the overall composite section. Square it, sum those. Y prime is equal to that column plus that column, which is 1 point something something 10 to the 6th millimeters to the fourth. Okay, does this make sense? This one's 4 something 10 to the 6th, 1 to 10 to the 6th. Yeah, because I've got so much more area spread away. Remember, moment of inertia is dispersal or spread of area. So this one's 4 times approximately bigger than this one, which makes sense because it's twice as tall. It's 120 tall, and it's only 60 wide, so it's spread out a lot more about the x-axis than it is about the y-axis. So those answers make sense. Moment of radius of gyration is real easy. Kx just I of the respective axes.